Tonight we're going to get into the surfactants, and especially the surfactants that are in the MCP. So we are going to start off with a little introduction, the Cliff Notes version of surfactants from Chris. And then Nina is going to give us a presentation on surfactants specifically within the MCP, their properties and their uses. And then we're going to stop for some questions right there. And then after that, Chris is going to go into a little bit more of advanced surfactant chemistry, and we're going to get into their properties, a little deeper. So with that said, Chris, if you want to take over. And I'm going to go ahead and mute everyone while Chris and Nina are presenting.
Okay, does that work for everybody?
Yep.
Okay. So practical science for conservators number 4, surfactants in the modular cleaning program. So what does this make you think of? And it's not your brain on drugs. If any of you remember the 80s public service announcement about taking drugs and eggs. Here's a hint, our drink for tonight. And the reason I show this is all modern surfactant science started with margarine. So the problem with the margarine when they first made it was that it would work fine spread on your bread, heart attacks notwithstanding. But when you cooked with it, the water and oil separated dramatically and you got spattering of the oil by the water when it boiled. So in the 1930s, well, it was invented in 1869, and in the 1930s, they found materials they could add to the margarine to keep the spattering down to a minimum, just like butter. And that led to the correlation of molecular structure with surface active agents. And this is the genesis of surfactants science, is all based on that. So surfactant agents, surfactants is a contraction for surface active agent. That covers detergents, soap, emulsifiers, dispersing agents, affinity surfactants, foaming agents, wetting agents, and surface tension breakers. So a surfactant is a molecule that has both a hydrophobic and hydrophilic end. And for that reason, they inhabit interfaces. One end of the molecule will always be repelled by the solution it's in. And here is our prototypical surfactant molecule, sodium lauryl sulfate or sodium dodecyl sulfate. This is the mainstay of cheap shampoo. Very foamy, nice lather. And it's got that 12-member carbon chain. And that sulfonate group is water soluble. So it's got the nonpolar hydrophobic carbon chain and the water soluble, water dispersible ionic portion of the molecule. So it's an anionic surfactant. So when a surfactant molecule is put into water or solvent, the compatible end goes into the water or solvent, and the incompatible end tries its best to get away. So I always think it's like a conservator. We're always unhappy. When we're doing research, we'd prefer to be doing treatment. And when we're doing treatment, we'd prefer to be doing research. So the same thing happens with, and we're never happy. So the same thing happens with surfactants. When they're in water, the one end sticks out, so wishing it was in solvent. When it's in solvent, the water compatible end sticks out, wishing it were in water. So as we exceed the amount of surface on our liquid, as we add our surfactant to water, and we exceed the surface area, where the surfactant can line up on the surface like we just saw here, something has to happen with that surfactant. So what it does is it forms micelles. And we have either the lollipop structure, or which forms into our micelle here, or with the hydrophilic and hydrophobic group. Or here's a drawing of sodium lauryl sulfate molecules, and you can see how the fatty part is all clumped to the middle, and the yellow and red are the water compatible parts of that molecule that are stud to the outside in an aqueous system. And that's a lower energy state. So this is thermodynamically favored to form these micelles. So there's the critical micelle concentration, which is that point at which we go from just studying the surface of the liquid with surfactant to actually forming micelles, and that's the critical micelle concentration. And one of the big takeaways that is incorporated in the MCP is that we want to be above the CMC, the critical micelle concentration, if we want to make an emulsion or some kind of a detergent system. If all we want to do is break surface tension, we can be below the CMC, or at the CMC. If we want to do anything with that surfactant, we might want to use 5 times, 10 times the CMC, but there's no reason to use more than that. It's doing its job, and it will, we don't want to overload the system with too much surfactant because we just have a problem clearing it afterwards. So we want to use in the range of 5 to 10 times the CMC. We can also characterize surfactants by the polar, the hydrophilic end. It can be non-ionic, anionic, or cationic. Non-ionic achieve their water solubility with ethoxylate or propoxylate chains, and those are compatible with water through hydrogen bonding with the oxygens on those propoxylate or ethoxylate chains. And the takeaway with that is they can be used at any pH. You don't have to worry. They're very versatile, and they behave well, play well with others. Anionic surfactants are actually characterized by a pKa. They're weak acids, and you deprotonate them to become water soluble. So there is a pH below which they will come out of solution and form a gooey stuff on the surface of your water. So traditional soaps are anionic, like when you boil animal fat in lye to make soap. So this is the ethoxylate and propoxylate chain. It's just polyethylene oxide and polypropylene oxide. And they form on the alcohol group on our base fatty part of the molecule and form chains depending longer and longer, the more it reacts. So another thing to consider is the HLB, the hydrophilic lipophilic balance number. And this is kind of a measurement of how strong a surfactant is, but it's really more empirical and kind of a flawed system because it was originally designed for non-ionic surfactants with a scale from 1 to 20. So typically a non-ionic surfactant will max out at a HLB of 20. It works so well that they decided to really mess it up and extend the range to 40 and include anionic and cationic surfactants. But the basic takeaway is a higher HLB number, more hydrophilic, more water soluble, lower HLB number, more hydrophobic, less water soluble. And as I said, it's kind of a measure of the strength of the surfactant, sort of. But we have to take that a little bit further and think about solubility theory and like dissolving like. So last thing I want to talk about is, or mention, is the cloud point. And non-ionic surfactants have this very peculiar behavior. As you take a 1% solution of the surfactant and warm it, there's a temperature where it'll, at its cloud point, you will see it go from a clear dispersion of that surfactant in the water to a cloudy mixture. And that's the cloud point. That's where the hydrogen bonding with the ethoxylate or propoxylate group flips around and it becomes less soluble as it heats up. Kind of very counterintuitive that things come out of solution as you heat them. But we'll talk about later that this is something we can really watch out for and exploit. And now it's Nina's turn. Nina, you need to unmute.
Hey, is that better?
We had a little bit of an error with our mute, so I'm going to remute everybody, and then Nina, I'll unmute you.
Okay, I'm assuming people can hear me.
There we go.
Perfect. Okay. So those of you who are of a certain age may remember the People in Your Neighborhood song on Sesame Street. And while I was working on this presentation, I was thinking, who are the surfactants in the MCP? And the song popped into my head. So we are going to meet the surfactants in the MCP very much the way Grover introduces us to them in the song. So in version 10.3, which is the latest version of the MCP, which you may or may not have, but even if you don't have it, you can still follow along with this talk. There are a total of 47 surfactants. In the typical workshop solution set, those are the sets that you would create while taking a workshop. There are usually about 7 surfactants, although that does vary. And there has been more variation in the surfactants than in any other of the components of the MCP. This is due to the wide variety of surfactants available from industry. And it's an advantage in that it yields a great variability, but it also can be a nuisance when you find a surfactant that you really like and then it becomes no longer available, which does happen. So choosing the right surfactant can be very daunting. And here we see Beaker considering his surfactant choices. So if you wanted to find where the surfactants were in the MCP, you would go to the initial MCP launch page and you would click on the components database, which is right here. And then you could click on a search bar and you'd get a drop-down menu and you could select surfactants. So that would be right here. And this gives you, I did a couple screenshots, and this gives you, starting with bridge, the first screenshot down to sodium lauryl sulfate, and then the second screenshot for the rest of the surfactants. Altogether, there are 47. In the typical aqueous set, this would be the aqueous set for just for traditional. I know it says traditional and acrylic, but it really is just traditional. You would have these 7 surfactants, and these are the surfactants that we are going to look at in some depth in this presentation, along with some others, but we're going to concentrate on these 7. So these are the surfactants in the basic MCP kits, and we'll meet them in the surfactants in the MCP in the order in which they would appear if you were doing a cleaning test. So as you scroll through increase and decrease surfactants, they're actually sorted by ascending HLB numbers in the sets. And again, these are the sets that you would make if you were at an MCP workshop. So EcoSurf EH6 is a surfactant in the MCP. And here we see Grover surfing. And if you were to go to the chemical information page, it would show you this, the chemical name, sort of that it's non-ionic, that it's surfactant. Sometimes it has supplier information here. This one doesn't, but sometimes they do. Short names and other names. And then, sorry, if you were to click on properties, you would go to this next page, and then that would say the common name, and here you see your HLB number, your CMC, and all the like. So EcoSurf EH6, the EcoSurf series is made by Dow Chemical, and all EcoSurf surfactants are advertised to be low odor, environmentally clean, and provide excellent wetting properties. And EcoSurf EH6 is used in industry for hard surface cleaning, textile processing, and oil drilling production additives. And this is the general EcoSurf molecular structure. This area over here that's in the parentheses and the N. So if you have EH6, this would repeat 6 times. If you have 3 times, and 9 times. Many of the surfactants have a title and a name and a number, and the number usually relates to the length of a repeating unit, like an ethoxylate chain within the molecule. EcoSurf EH9 is a surfactant in the MCP. And you'll see that the Muppets are generally interpreting the use or the name of the surfactant in some way throughout the presentation. And again, this is the chemical information page. Again, it'll show you it's a non-ionic surfactant. And here are some of the parameters and properties. It has an HLB of 12.5. And EcoSurf EH9 is used in industry for removal of oily soils. It is advertised to have superior wetting, rapid dissolution, and low odor. And industrial applications include hard surface cleaning again, paper and pulp industry, and paint and coatings production. Surfonic JL80X is a surfactant in the MCP. And here is its information. Again, it's non-ionic. Its HLB is 13.1. It's made by the Huntsman Corporation. And you may know Surfonic JL80X. It is the replacement for Triton X100. And Triton is a surfactant that almost every conservator is using is familiar with. Triton and Orvis were the most two common surfactants that I learned about in grad school in the early 1990s. And industrial applications for Surfonic include metal cleaning operations. It has low foaming properties, which make it useful for conservation applications. And here is the molecular structure for Triton. 80XLN, where this repeats 8 to 10 times, and Surfonic, where it repeats 6 to 8 times. So you can see they're very similar structures. And depending on when you took the MCP, you'll either have the Triton 80XLN or the Surfonic JL80X in your kit. So Marley Paul is a surfactant in the MCP. And here's the information, sorry, 16, 18, 25. There are about 1,000 different Marley Pauls. So you make sure you get this one. It has an HLB of 16.5. It's no longer production, but is still available from Kramer Pigments. Marley Paul 16, 18, 25 passes all German environmental standards and is readily available in the EU. It is a non-ionic surfactant used in industry and personal care products, coatings, and inks. And Chris says that when he teaches the MCP in Europe, this is often one of the surfactants that's very easy to obtain in Europe. So that's why it's included in this in the kits. So sodium deoxycholate is an unusual surfactant in the MCP. And here's its structure. It's a surfactant salt. It is not actually a non-ionic. And here is some more information about it. Its HLB is 17.6. Sodium deoxycholate is a natural occurring in digestive bile where it is used to emulsify fats in the body. Sodium deoxycholate affects the protein of cell membranes. In the medical field, sodium deoxycholate can be injected below the skin to dissolve fat cells in plastic surgery procedures. In the pharmaceutical field, it is used in conjunction with many drugs to help absorption into the body. Under 1%, it can act as an anionic detergent / surfactant, and the common source of industrial sodium deoxycholate is bovine bile. In the MCP, sodium deoxycholate is the only pH-dependent surfactant. Within the MCP, sodium deoxycholate is only available with the pH 8.5 buffered set and is not soluble at a lower pH than 8.5, and we no longer use pH above 8.5 in the MCP. And it's mostly used to create resin soaps that can reduce discolor and oxidize varnishes. And it can be used with or without benzyl alcohol as a co-solvent. And here's its molecular structure. You can see it's different than the man-made surfactants. It's got a lot more three-dimensional structure. So Bridge S100 is a surfactant in the MCP. And Bridge is a non-ionic surfactant. And it has the highest, has a higher HLB than sodium deoxycholate. So that's why it's presented right afterwards in this. If you were to scroll through your surfactants while doing a test, it would come in after the sodium deoxycholate. In industry, Bridge S100 is used to support the formation of emulsions with palm oils and personal care products such as antiperspirants, deodorant, shaving creams, and sun protection. Unlike most surfactants in the MCP, Bridge S100 is a hard, waxy solid that can be challenging to dissolve into solution. It also can grow mold into solution and often needs a little bit of a fungicide in the solution, similar to the pH-adjusted waters. If you want to store it long term. And Bridge S100, formerly known as Bridge 700, is manufactured by the Croda Corporation, and the website does offer the possibility of ordering samples. And here's its molecular structure. And this, in the Bridge S100, this unit right here would repeat 100 times. The Pluronic F127 is a surfactant in the MCP. And here is Pluronic, also called Poloxamer 407. It's non-ionic. Here's its tiny structure here. It's a surfactant. It's also a solid. And it has a high HLB of 22. And even though it's non-ionic, it does have an HLB of 22. even though Chris said that HLBs are only supposed to go up to 20 for non-ionic surfactants. So poloxamer 407 trade name Pluronic is a hydrophilic non-ionic surfactant. It is widely used in cosmetics industry to dissolve oil into water. Pluronic is also used in multi-purpose contact lens solution and mouthwashes. In the medical field, it is used for vascular and neurosurgery, where it's used to help align severed blood vessels. And it can also be used in the process of bioprinting due to its unique property of forming a gel, 30% concentration at room temperature, and forming a liquid when it is chilled to 4 degrees Celsius. And it's used as a substructure for hydrogel in that case. And again, as noted before, it has an interesting property of being a gel at room temperature and a liquid when cooled. And there's Beaker considering that interesting phase phenomena. And here is its structure, which I'm not really going to comment on. Chris and Luke can talk about that more. So here's just sort of a summary of what we just discussed, of the information that you can find in the MCP with all of these surfactants that are in the normal kits, EcoSurf, EH6, sorry, non-ionic with the HLBs, and you can see the HLB values are ascending here. And I mentioned before, sodium deoxycholate is the only one that's not a non-ionic surfactant. So there are a couple surfactants that are not in the kits, and these can be harder to obtain these days, but some of them are still really useful. I have, my first kit is from 2005, and I have some surfactants that are no longer used, are easily obtained. But there are also some that there are also some that aren't mentioned in the section on the kits that can be used for making resin soaps, which we're going to go over here. So Mapon 4C, which is also a surfactant salt, and it has it doesn't have an HLB that's listed, so that's why it's not mentioned here. And it's potassium cocoyl hydrolyzed collagen, or Mapon 4C. It's a surfactant salt based on a collagen protein. It's an anionic surfactant. In industry, it's generally used as a gentle and mild cleanser, commonly used in things like baby shampoos, luxury facial cleansers. It is referred to as a foaming collagen, and it can be very useful because it's the only surfactant that can help in the reduction of proteinaceous materials. So it can be useful in removing thin animal glue layers. It also makes a great surfactant that can make kind of a great, I found, synthetic saliva. If you don't want to clean a giant thing with saliva, a buffered 7.5 Mapon solution is really very similar to saliva in its cleaning action. It's no longer available commercially, although a conservation support system still listed available, and I have a huge container of it. So if you really have a particular use for it, contact me and I can send you some. Abiatic acid, and here's its structure. It has an HLB of 8.2. And abiatic acid is a naturally occurring acid present in trees, especially pine trees. It's found in rosin, and traditionally rosin is used to maintain musical instrument bows. And rosin is also used in varnishes and resins and soaps. And it's very similar to its structure of a natural resin like terpenoids, xanthoids, and mastic. So it can be used as an active ingredient in a resin soap to help remove varnishes. Aluritic acid. And it is a surfactant and an acid, as it says here. It has, the HLB isn't listed, so it probably doesn't have an HLB. And it's naturally occurring substance and is the major component in shellac. And in industry, it is used as a perfume base, and it has a musky odor. And it can be used to create resin soaps that would help to reduce shellac coatings. So there are a few surfactants that are used in microemulsions, and I'm not going to talk too much about microemulsions because it's really Luke's area of expertise, but it's worth mentioning that EcoSurf EH3, which is similar to EH6 and EH9, but has a shorter ethoxylate chain and a lower HLB, 7.9, is useful in making microemulsions. NaDOSS, or dioctyl sodium sulfosoconate. And here's its structure. It is a surfactant salt. It has an HLB of 10.9. NaDOSS is also known as aerosol OT detergent. It has many industrial uses, including food additives, thickeners, and stabilizers for things like spreadable cheeses and salad dressings. It is useful in the formation of microemulsions because it can do reverse micelle encapsulation. In the pharmaceutical field, it is most commonly used as the active ingredient in laxatives such as Colace. It has been found to be safe and non-toxic in most land species, except for reptiles in captivity. And I'm assuming wild reptiles don't get laxatives. So it has some toxicity to marine species, especially crustaceans in saltwater and trout in freshwater. So don't dump it down the sink. Triton GR7M is a surfactant for microemulsions. Here's its a surfactant salt as well. Here's its information in the MCP and the properties. And sulfosoconate, it's an anionic surfactant. It's soluble in oils, but not in water. It's stable in moderately acidic and alkali solutions. It's an amber colored liquid. And in dry cleaning, it's used in industry, it's used for dry cleaning, agrochemicals, paints and coatings, and olified chemicals. And these are the surfactants that we no longer use. So Orvis, or sodium lauryl sulfate, is no longer in the MCP kits. Although sodium lauryl sulfate, trade name Orvis, still appears in the MCP, it is not included in the kits. It is ubiquitous surfactant and is the active ingredient in many shampoos and detergents. Sodium lauryl sulfate foams in contact with water and agitation. While this foam formation is great in shampoos and household cleaner, it is not a great feature for conservation applications. And if for any reason you need Orvis, it can be bought at farm supply stores as it is often sold for washing horses. And Triton X, one of our favorites, is also no longer used in the MCP kits because it makes Kermit very sad. It was the first surfactant many of us used in the 1990s and has been replaced by Surfonic JL80X. Triton X was found in runoff water. Unfortunately, it is an endocrine disruptor and has the unfortunate property of mimicking estrogen and causing frogs to become females. Amphibians are very vulnerable to changes in their ecosystems and are often considered indicator species for environmental toxins. And here is its structure. You may notice that it has a benzene ring in the middle, which is one reason why it was so effective. This benzene ring can really help to cut greasy substances, and one reason why the newer Tritons and Surfonics may be not as successful as in removing grime as the older Triton X. So Triton is a good example of the variability of surfactants within the MCP. Triton X has been replaced with Triton XL80N, which was then included in the early sets, and then Triton XL80N was replaced with Surfonic JL80X. So in all seriousness, I hope this introduction to surfactants in the MCP has helped you differentiate among them. And I wanted to confess that I rarely use surfactants in my daily practice and with the MCP because I sort of test by doing pH, buffers, and then chelators, and then something usually works great, so I don't bother adding in a surfactant. And I was always kind of confused by them, and I didn't want to get attached to one that wasn't used or going to be available later, so I just kind of didn't use them. But in preparing this talk and getting ready to really talk about surfactants, I forced myself to use them. So I wanted to talk about how they can be a useful tool in characterizing a grime layer. A grime layer that responds well to bridge is likely to have an oily component. So as bridge S100, you may remember, is used to emulsify palm oils. As you test, you may know what you are trying to remove and tailor your surfactant accordingly, but you also may learn more about the grime layer as you test different surfactants. And let's, like I said, for example, if, sorry about the two Fs there, bridge S100 is effective, you can deduce that the grime has a greasy component. So I wanted to do some case studies to kind of show you what it's like to use the surfactants and see if there's any differences. So I tested some paintings that I had lying around the studio, and everyone relax. It's not a Titian. This is a copy that my grandmother did at the Met when she was a little girl. And at the top we have saliva, which of course worked the best. And then the EcoSurf EH6, EcoSurf EH9, Triton. I had Triton XL80 and not Surfonic, and bridge S100. There's a close-up of the swabs. Here's a close-up of the cleaning test, and you can see none of them really made any difference on the surface of the painting. So then I did another dirtier painting, also by my grandmother. And here you have the distilled water, EcoSurf, EcoSurf H9, the bridge, and the Triton. And here are the swabs that go along with that. And all the swabs are sort of equally gross. So it's hard to tell which worked the best. I will say that in this last one, although the bridge looks like it cleaned better, it actually had kind of a gritty feel when you were using it. And I don't know that I would actually choose that if I was doing a big cleaning with it. Today, I tested a very, very dirty painting with super, super dark oxidized varnish. And you can see nothing really did anything except for the bridge S100 got a little dirt off, and you can't see any difference in the cleaning tests. So then I did an area on a lighter area with the bridge, and I did get quite a bit of grime off. And then just above it, I decided to add, since the bridge worked, to make a resin soap. So this is the pH 5. It's hard to read, but it's the advanced MCP where you add everything, but it's to make a resin soap. It's pH 8.5 buffered with bicene, the DTPA as the chelating agent, and then 2 surfactants, the sodium deoxycholate, and the bridge S100. And that actually got this area so clean that when I went to rinse it, the swab came up completely white. So that's a pretty cool cleaning. If you added a benzyl alcohol co-solvent, it would probably work even better. So here are some reading materials about surfactants, and these are great, especially for those of you who prefer their surfactants without Muppets. An AIC wiki about surfactants. It really kind of focuses on the health issues, but it also has all the information about HLBs, comparative non-ionic and anionic, cationic. And then this is an article that Chris wrote for WAC newsletter several years ago, but it has a lot of information about the surfactants in it. And I'd just like to thank everyone for their attention.
Okay, so we're going to stop for our first question break. So that was a lot of information. So if you have questions, keep throwing them in the chat. Okay, so our first one was from Kristen, who said, have you noticed that basically these names are changing all the time? And have you noticed that the surfactants that we commonly use change their names? And then she later said, yeah, I see that they do. So yeah, these surfactants change constantly. There are hundreds of thousands of surfactants available in the market. They are extremely easy to make, and they're extremely easy to make new ones. You can just add a new methyl group to a surfactant, and now you've got a whole new surfactant to market. So yeah, and there's tons of surfactants in the industry, and they're constantly changing. Luckily, most of the ones we use stay the same. And luckily, one thing we're going to get into is the class of surfactants, the families. And you can start to see that, even if your favorite surfactant is discontinued, it's not that big of a deal. You can find a replacement pretty easily. You just have to look for it. Okay. So Susie asked, I understand that oxgall used in paper marbling contains a surfactant. Any idea what it might be? And then Sarah replied, oxgall. She's also curious in that Wikipedia says it contains cholesterol, lecithin, taurocholic acid, and glycocholic acid. And would any of these be responsible for its action?
Well, I believe it has, I believe oxgall is from the gallbladder of an ox, if I'm not mistaken. And it includes deoxycholic acid, among others. So it's got that whole family of cholic acid, deoxycholic, hydrodeoxycholic. So it does have deoxycholic in it, which is why it would work for cleaning. And all those are surfactant-like in nature. It's the sodium salts of all those.
Yeah, and those are interesting. They actually are a product of cholesterol metabolism. They have a very similar. Well, they do have a steroid structure, so that's really what it is. Just like cholesterol is a steroid. Let's see. Brooke asked, can Triton GR7M be used on distemper paints?
GR7M is the NA-DOS it comes in premixed in mineral spirits and with a small amount of ethanol added. So it works for, it's not water soluble by itself. I'm sorry, I take it back. NaDOS is slightly water soluble, so you can clear it with water. Normally we use it to make microemulsions, and these are the Dow microemulsions that were made as part of the CAPS project. And it makes some nice microemulsions. And other than having a more surfactant than would be ideal, yes, you can use them on water sensitive surfaces. You can control the amount of water, and the water can have adjuvants in it, so it can be pH buffered and have chelators and all that. Clearance is fairly easy, but on something that's really porous, there's always the question of, can you get it all out again? So I'm always cautious with something that has that much surfactant in it to put it on a surface that you might not be able to rinse it all out in. Bronwyn Ormsby and I have a disagreement about if you have to have a little bit of isopropanol in your clearance solvent, which would be normally mineral spirits or shell sol. I think you do. She has studies to prove you don't, but I'll stand by my statement that about 2% isopropanol makes it better. So and you don't have to buy the Triton GR7M. You can just buy NaDOS and make it yourself with mineral spirits and a little ethanol.
Okay, and Michael asked, do you know why Trident XL80N was replaced by Surfonic?
It wasn't actually replaced in the commercial term. Dow replaced or made a friendlier version of Triton X100, more biocompatible friendly, which was the XL80N, and they discontinued it. So Scott Blair at Conservation Support Systems found the Surfonic JL80X as being very, very similar to the Triton XL80N. So that's kind of the begats of the linear alcohol ethoxylates.
Yeah. And someone asked if you've ever used Tween 20.
I haven't, but I know it's very popular in Europe and for making reverse emulsions. But I haven't, so that's bad on me.
Let's see. And then someone asked, why do you not need a surfactant with Pemulin?
Okay, Pemulin is a polymeric emulsion stabilizer. So the whole point of it is that you don't need a surfactant. So it was formulated to make sunscreen, and people were having allergic problems with the surfactants in the sunscreen. So they formulated Pemulin to be a polymeric structure that had virtual micelles in it. So you just throw solvent in and stir, and it makes an emulsion, a conventional emulsion. And that's the beauty of it. So you don't need a surfactant as far as forming the emulsion system.
Right. One caveat to that is that you don't need a surfactant to form the emulsion system. It doesn't necessarily mean that the Pemulin is going to attack the greasy grime layer the same way as surfactant would. There will be some interaction, but those are not equivalent. This is for forming your emulsion, not necessarily for cleaning your surface and serving the same purpose.
And the note to add for adding a surfactant to one of the polymeric emulsion stabilizers is that when you use a little milk frother to stir up your xanthan or Pemulin, and you have surfactant in there, it froths like crazy. You get a big cup of foam. So you always add your surfactant last after you've whipped it up.
Okay, and then there's a conversation going on about synthetic saliva. So someone saw Nina's cleaning test, I'm guessing, and mentioned that saliva seems to work really well, and sometimes it works the best. So
let me answer that. I work in private practice completely on my own. I'm still using saliva because it's just me on my own. So I feel it's COVID safe. A long time ago, I did sort of make what I called synthetic saliva by using the MCP to create as close to saliva just by empirically for a large project that I could really only clean with saliva. And I found that pH, I think it was pH 7.5 buffered citrate solution with Mapon acted very similar to saliva. just in terms of the way it cleaned.
And that makes a lot of sense. There is citrate in saliva. The pH is, I think, 7.4. And saliva has enzymes in it to some extent, and the Mapon pulls in those proteinaceous materials. And the one thing to mention is that Mapon is still being made. It's just that the company that makes it will only sell it in 55-gallon quantities. So
I do have like a quart jar, and you really only need a couple drops. So if anyone is making that, how much Mapon percentage wise? So to answer your question, you go into the MCP and you do the test, you run a test, you create a cleaning test, and you use the formula that the MCP gives you. So you don't need, so it'll tell you. So if you select pH 7.5, and then you select citrate as your buffer, and you select Mapon as your surfactant, and you hit clean, it'll do it. So Mapon's not in there anymore, right? So
it's not in the solution set, it's in the database. So you can just add it. If you have it, you can add it back into the solution set.
Right. So I can, if anyone's interested in actually working on that, I can make you, I can help you do that with the MCP.
Yeah, and with a lot of these surfactants, a little bit goes a long way.
Right.
With Surfonic JL80X and 100 milliliters of water, it's literally 3 drops of Surfonic.
All of the MCP surfactants are calculated to be at 10 times the CMC, correct, Chris? And then they're also concentrated 5 times above that for the stock solutions.
Correct.
So it's a little bit of math, but it's doable if you sit down with the MCP and kind of work through it.
And in the case of Mapon, we don't have it CMC, so we use it at 2%, which is probably too high. But that's what people were using when I first formulated the system. So we use it at 2%. So the concentrate is 10%. So you do actually use a fair amount of it when you make up a bottle.
Yeah, and one thing that's really nice about the MCP when you're working with surfactants, if you're particularly worried about clearance and how much surfactant you're using, the surfactant that you put in doesn't really affect the pH buffer in the chelator or whatever else you're doing. So you could literally just cut the amount of surfactant down, by 50% by a third. So if you want 3.33 repeating CMC surfonic, just put 1 drop in with 100 milliliters of solution. You can cut that down a lot. And you can also play with concentration that way too.
Just make sure that when you're doing it, you're still using the 5 component system. So you have to add enough water to make up your total volume. If you're not adding a surfactant from the solution, if you're just adding a couple drops in your final solution.
Okay, it looks like we have one last one, and then we'll get to the next lecture. Do you know something about the problem of residues of ethoxylated surfactants? Oof, can they form cross-link like cicative oils?
I don't believe so. I think this came out as a misunderstanding. I may be wrong, but there was, due to environmental and health and safety regulations, they would put on the MSDS, the SDS, the amount of potentially free ethylene oxide. And ethylene oxide can react to the surface. So there was a tiny, tiny amount of ethylene oxide listed. And I think people said, oh, the ethylene oxide can be a problem, even though it's like 0.005%. And I think that's where this came from. I'm not sure about that, but that's my understanding.
Okay, so, I mean, if you're worried about residues, again, you can cut down the concentration again, use a lower CMC, but also with the alcohol ethoxylates, they break down quite readily, sometimes within half an hour, a few hours, and they can be cleared later. So I've personally used some ethoxylates as surfactants, notice a residue after, you know, the object dried, and then came back and just cleared it, and it's just right on the surface, and there's really no harm, no foul there. Okay, so I think we're ready for Chris's deep dive into surfactants.
All right.
Luke, are you going to mute everyone again?
Everyone should be muted except for the hosts.
Okay, so let's talk a little bit about how a surfactant works. As we talked about earlier, a surfactant has a fatty end, a hydrophobic or lipophilic end that interacts with that surface when we're trying to do detergency. And it has a water-compatible hydrophilic lipophobic end that interacts with your water. So we're talking about cleaning something in an aqueous system. And in that water, we talked about how micelles form with the fatty end at the center of the globule and the hydrophilic end studying the outside, excuse me, that's the micelle. So here we have more of those pictures of micelles. So we can form that micelle around dirt and facilitate dispersing that into water. That's detergency. We can also use them to make emulsions by putting the solvent in the middle of that micelle, a solvent that's compatible with the fatty part of that chain. And we can make reverse water and oil emulsions by putting the surfactant in solvent and putting a water in the center of the micelle. So this is a really important diagram. This kind of explains it all. So we have our dirty stuff, or yucky stuff here. We have our substrate. And unlike most cleaning systems, we care a lot more about the substrate than cleaning engine components people do. So first we have enough surfactant to reduce the surface tension. So we have our surfactant lined up on the surface. We have an excess of that. So we form these micelles with the lollipop on the outside and the stick on the inside. But the other thing that happens is that surfactant will form a layer on our substrate and on our dirty stuff. And this is one of the critical aspects. It's the compatibility between the fatty part of the substrate, of the surfactant, and the substrate that gives an indication how well this surfactant is going to pick that material up. So this is going back to solubility theory, and literally like dissolves like. The more alike that fatty part of the tail of the surfactant molecule is like a grime layer, the more readily it's going to be attached and pull back up into solution. So here we have our surfactant attached to our greasy, grimy soil. It's reducing the surface tension, allowing that soil to roll up and end up in the middle of the micelle and float away. So when we're talking about micelles, we already mentioned there's a critical micelle concentration. There's also the aggregation number, which is roughly how many surfactant molecules form a micelle before a new micelle is formed. And if we know both of those, we can actually calculate the molar concentration of the micelles. So even though it's not a thermodynamic property, the CMC, the critical micelle concentration, is a real property. When you hit the CMC, all these properties change: surface tension, conductivity, viscosity, dye solubilization, light scattering, refractive index, osmotic pressure. So they either stop changing or they begin to change. So here we see some of these changes. Here's the CMC, and you can see how, for example, turbidity. There's no turbidity until you hit CMC, then all of a sudden the turbidity goes up. So there's particles in the solution as opposed to being on the surface. Osmotic pressure goes up until you hit the CMC, then it levels off. So all these things, surface tension, as you add surfactant before the CMC, the surface tension goes down. And then when you hit the CMC, the surface tension doesn't change anymore because you've filled up all those surface of the water with the surfactant molecules breaking that surface tension. So the aggregation number is roughly how many surfactant molecules fit into a micelle. So this is a sodium lauryl sulfate micelle with 12 sodium lauryl sulfate molecules forming the micelle. The aggregation number for sodium lauryl sulfate is between 68 and 101. So imagine what this would look like if I'd been patient enough to put 100 of these diagrams together, it would be this massive fatty blob in the middle, studded with these water-soluble yellow and red blobs. So let's talk about how we can exploit this like dissolves like. And these are referred to as affinity surfactants, which include resin soaps and some other systems that Nina mentioned. So sodium dioxycholate, sodium albutate, and sodium alurate are all can be used as resin soaps. And here's the Lego model. We have our substrate that has a certain pattern on it. We have our surfactant that matches that structurally. And so we can pick up the red Lego block with the blue Lego block. We can snap them together and pick them up. So that's the basic idea of a resin soap. It's like dissolves like. So here we have abiotic acid and deoxycholic acid, resin soaps. And here's the major component of Damar, which I can never pronounce that right. So the acid part of Damar. And we can see that there is some structural similarity here, and the deoxycholate will actually kind of sit down like a Lego block and help pull it up. The abiotic acid will as well. In practice, I prefer deoxycholic acid because the abiotic acid usually doesn't work as well, although one time I had it work better. But also the abiotic acid is a dark brown, mucky stuff, and you can be using it, applying it with a brush, watching what's happening, seem like you're getting all this stuff off. And when you clear it away, nothing's really changed because you just figure all that brown is coming up and it's actually just the abiotic acid. So I personally use deoxycholic acid, often with N-butanol or benzyl alcohol added as a co-solvent at about 2 to 4%. Other affinity surfactants, Mapon 4C, which I mentioned is hard to get. And as Nina said, it is, a cation, anionic surfactant based on animal protein. So like dissolves like, we can put it on a thin layer of animal glue and pull that animal glue up into our solution, which normally wouldn't respond to water or would respond very slowly. And this can be great for cleaning a painting that's been glue lined, where the glue has kind of come through and is on the surface of the painting. It's not so active that it'll undercut the ground or size layer, but it will help pull up that little bit of glue residue that might be left on the surface. And then there's Ethofat 24225, which has been discontinued, although some people still have some left. I have a little bit, not enough to share. But that's basically a non-ionic resin soap. It's a really crappy resin soap, but if you need to work at a lower pH, it's your only choice. So sometimes it actually works very well. So the alkoxylated linear alcohols, as Nina talked about, Bridge, S100, Triton, and Surfonic. And they're basically all variations on the same theme. There's a straight chain linear hydrocarbon. Here the Bridge has 1, 2 plus 16, so 18 carbon chain. And the Triton XL80N has 1, 2 plus 8 to 10, so 10 to 12. The Surfonic has 1, 2 plus 6 to 8, so 8 to 10. I realize that's a little confusing, but it works out. And the Bridge has that 100 chain ethoxylate group, and the Triton Surfonic, we don't know the numbers, but there's a ethoxylate group first and then a propoxylate group second. And if we look at these numbers, we see CMCs are all more or less in the same place. We have HLBs going from 18 to 12 to 13. But the thing I want you to look at is the difference in the cloud point. So if we go back to the cloud point, the maximum detergency for a surfactant for non-ionic surfactant comes just before separation at the cloud point. So you want to bring it just above the cloud point. I'm sorry, just below the cloud point. That would be bad. Bring it just below the cloud point so the surfactant's still evenly dispersed in the aqueous phase. It's not separating out. and it will have the strongest detergency. So we want to bring that, we would like to have our cloud point as close to where we're working, just above our ambient temperature if we're working inside. And there's some things we can do to bring that cloud point down. We can add citrate. We can add ammonium ions. We can add sulfate. We can add these ionic salts that will suppress or bring down the cloud point even further. So what does that mean? Let's look at EcoSurf. Here we have that structure for EcoSurf. It's got that kind of weird bifurcated structure, and then the ethoxylate chain, 6 and 9 ethoxylate chain, and we don't know what the propoxylate chain numbers are. And if we look at the cloud point, we see the big difference between EH6 and EH9. Now, in theory, EH9 would be a better surfactant because it's got a higher HLB, so more detergency, higher HLB. Otherwise, everything's the same. It's the same structure, it's just the longer ethoxylate chain. But in fact, often you'll find that the EH6 works better. Why is that? That's because its cloud point is lower. And especially if we're using it in conjunction with a citrate system, where we bring that cloud point down even further by adding citrate ions and also our buffer ions. If we're using a buffer solution, we're bringing that cloud point down closer and closer to being just above room temperature. So that's why EH6 often works much better, even though its HLB would tell you that it's not as effective. Here's pluronic, F127, and we're almost done. This is the pluronics are a fascinating material. They're just ethoxylates and propoxylates. There's no fatty thing there. And as Nina mentioned, this is the active ingredient in Listerine mouthwash, one of the active ingredients. But what's interesting about these is as they're exposed to light, that ethoxylate or propoxylate group break off. So as this material is exposed to light, we lose ethanol groups if it's a propoxylate chain, an ethoxylate chain, and isopropyl groups if it's a propoxylate chain. And slowly with exposure to light, these materials chop down and chop down and chop down. And in the case of the pluronics, they chop down and chop down and chop down until there's nothing left. So I don't know how long that takes. I'm guessing it's not really fast because you can have the stuff in a jar and it doesn't go away. But ultimately, in the fullness of time, the pluronics will just disappear from a surface with exposure to light. The other interesting thing about the pluronic is, even though it's a non-ionic, and remember I said that non-ionics have their HLB at 20, the pluronic has an HLB of 22. So it's kind of unique, being kind of a super non-ionic surfactant. And here's my last chart, my last slide, PowerPoint stack, here's Triton X100 with exposure to light. This was done at Winterthur years ago. And with more exposure to light, these are the lengths of the ethoxylate group. And we see that they're going down and down and down on exposure to light. So we're just shifting that family down, and it's becoming a smaller and smaller molecule. So that's what happens with the pluronics. And that is it for me. So take a breath, ask questions.
Yeah, so if you want to put questions in the chat or unmute yourself, you can unmute yourself and just talk to us. Well, I'll ask you guys a question then. If you had a greasy soil on a surface of a painting, would you use a surfactant with a high HLB, a low HLB, or something in the middle? Where would you start?
Let me add a little bit of a side note to that question. One of the things that was revealed in the conference and subsequent publication of Dirt and Painting Separated was that as a dirty surface ages, surfactants become less and less effective because essentially calcium and magnesium ions glue the oxidized surface of the paint or varnish to the oxidized grime particle. So fresh grime, you can use a surfactant. Old grime, you usually have to throw a chelating agent in to take that calcium or magnesium ion out and allow the dirt to float away. So Luke is talking about fresh dirt.
And I would add that with the testing I did with just the surfactants, they were not effective. They really aren't.
And that's because of that calcium locking them down. And the moment you throw a chelator in, they're going to wash right away.
So Luke has made it so that you can unmute yourself, I believe. So you can jump in and we can have pandemonium until it gets crazy, and then we can remute everyone. So if people will remember, certain of the surfactants mentioned were used for cosmetic industry, for helping to emulsify oily things into not oily things for cosmetics.
Okay, I'll begin. When you're talking about soot on a painting, and deoxycholate is always really good, but that's just it. If it's old soot on a painting, through years and years, is it possible that some of that soot has combined with some of the pigment? And it's hard to get that off a surfactant or with anything. It's just the pigment comes off too.
I don't think it's the pigment it's combined with. I think it's more a case of soot is actually a fascinating structure. It's a polyaromatic, it's a particle that's covered with polyaromatic hydrocarbons. So benzene rings stuck together, and that has a solubility parameter. So that will be sort of compatible with the oil. So it's not the pigment it's interacting with, but it might be the oil layer on an oil paint. And I think it does migrate in. And in the case of acrylics, with changes in temperature and humidity, the surfactants that come up and down will pull the soot into the acrylic paint film. One of the reasons Triton X100 was so good is because it has that aromatic ring in it. And that is like dissolves like. The aromatic ring in the Triton and the polyaromatic hydrocarbons on the soot particle are very compatible. So Triton X100 is actually really good at either dispersing carbon black in a jar, which shows how well that interaction works, or will be a better choice for removing sooty material. That said, it's ecotoxic and not so good for us either. So be very careful if you do use Triton X100.
Right.
We
So, go ahead.
Go ahead. No, I was just going to say it's just horrible because I was just telling my colleague we would use it on sculptures, large sculptures, and we have vats of that stuff. Vats.
Mhm.
Like, what are we going to do? I was just thinking about that. Like, what do we do with this stuff?
Hazmat.
Yeah, we're just going to have to send it out.
You probably have enough to feminize all the alligators in the Everglades.
Absolutely.
Also, in a roundabout way, Chris kind of answered that question by talking about the benzene rings. So one of the things that was mentioned earlier is that the HLB of a surfactant is determined by the ratio of the polar head groups to the nonpolar tail or the carbon chain. So for really greasy, sooty materials, a lower HLB can actually be very effective. A lot of times when you read the literature, you'll say, if you have something really greasy and oily, you want something with a really high HLB, because a high HLB means high cleaning power. and that's not necessarily true. So one of the kind of concepts is that just because the HLB is high doesn't mean that it's a good match for your particular soiling material you want to remove. And one of the things that we talked about was you can actually use surfactants to characterize what kind of soil you have. So like Chris just said, if you are using a surfactant on a surface that you see is soiled and you see that there's soot on it and it's not coming up, well, now you know you have an aged soil there and you can start to approach it a different way. One of the things that we talked about were our top 3 surfactants. And the MCP does a really good job of narrowing it down for us. So like we said, there are hundreds of thousands of surfactants out there. And so the ones that I kind of tend to stick to are EcoSurf EH6 and Surfonic. And then I would have thrown Triton X100 in there, but I'm still trying to think about what my third favorite would be. But those have pretty moderate HLBs. They're, between 10 and 13, which is a pretty good place to start generally for a cleaning problem. You're not going to do any damage to it by starting around, 10 to 12 or something like that. It's a pretty mild surfactant.
I would make the third one either the Bridge S100 or the one I'm leaning towards more for higher HLB is the Pluronic F127.
That would be my third, would be the Pluronic.
I haven't tried Pluronic because I don't have any, but I would say that the Bridge S100 it works really well, and it's great if you find a MCP solution that works nicely, but it just doesn't, it's not even, or it feels a little gritty when you swab. The Bridge can often help just make it a little smoother and a little bit more even.
And I think what that, I mean, the thing I haven't said yet, which I think is my summary for everything to do with surfactants, is trial and error.
Yeah.
I mean, you can have all these great theories about what's going to work and what's not. And sometimes you're right, lots of times that you're completely wrong and something else will work really well. So that's one of the strong powers of the MCP with those concentrated solutions. You can test every surfactant you have in a matter of minutes and see if a surfactant is working, then you can narrow down which one's going to work best.
I hope that my part of the aim of my talk was to sort of tell you what they're used for in real life, can make them feel like you know them a little better, so that when you are testing and there's 5 surfactants on top of the 5, you're up to your 25th permutation of things, you'll feel a little more comfortable just diving in and trying the surfactant as well.
Can we just talk about nicotine glazes on surfaces? Because I come across that all the time, and spit swabbing large swaths of walls with nicotine glaze on them is just not feasible for me, unless I just want to utterly dehydrate myself. Would you think that the Surfonic would be the best one for that?
Well,
or would you?
I can tell you that painting that I showed the tests of today, I didn't I mean, it's super, super dirty, but when I was using both of the EcoSurfs on it, I could really, really smell nicotine coming up. Now,
Grandma's ashtray, my favorite smell. It's disgusting.
So I often think that, I could be wrong, but I often think that the water is really what helps with the nicotine, that you might not need a surfactant. But I was surprised at how much nicotine I smelled with the EcoSurf. So that was just a little observation.
I mean, I'm sorry, just to carry this on, then I'll shut up. But I found actually that nicotine can be layers and layers and layers, particularly on sealing surfaces.
Right.
And so you'll get this phyllo dough of ashtray, dirt, ashtray, dirt, ashtray, dirt. And so I didn't want to put too much water on the surface. So if I can kind of get it within a couple shots, as opposed to going back in and, does that make sense? I'm so inarticulate right now, but that's why I was thinking the surfactant might be good.
Yeah, I mean, a surfactant would be good to try, but that kind of illustrates one of the difficulties with what we face on a day-to-day basis, which is that we aren't working with pure nicotine, right? There's a bunch of other stuff in there. There's skin cells, there's dirt, there's, metal ions. There's all
Yeah.
kinds of stuff in that soiling layer. So a surfactant is going to definitely help with a lot of that stuff. But if you follow the MCP, you keep things at 10 times CMC. You're following the protocol. It's safe to test it. So it's like you might as well go ahead and test it because it can make a huge difference. In my talk next week, I'm going to show some examples of going from literally no cleaning effect, changing the surfactant slightly, and then just blasting material away. So it can have a really big effect on what you're doing. So, and there's no harm in trying it if you're approaching it intelligently.
Thank you guys so much.
Question, and that is, does anybody present know what the actual proportion of nicotine is in cigarette smoke? And the corollary of that is, how much then is nicotine contributing to the solubility characteristics of what we encounter as cigarette smoke deposition?
I believe most of the cigarette smoke deposition is what they refer to as tar rather than nicotine.
Exactly.
Nicotine is incredibly toxic. So if that were pure nicotine and you touch that surface, you would probably die. So there is some nicotine, I understand, you can see it with infrared spectra, but nicotine is really bad stuff. Besides being besides inhaling it, it's really toxic material. And Brooke, you've got a baby. You've got all the spit you need.
That is a fair point in all forms. All forms.
All right, so we got a question from Sarah. This is actually an awesome question. So they asked, anyone care to share their favorite surfactant for cleaning outdoor sculptures? I've seen Orvis used once on bronzes, and it was odd seeing a bronze horse being cleaned with it rather than a real one. And what would you use now that Orvis isn't commonly used?
There's
Orvis-
nothing wrong with Orvis.
Yeah, go ahead.
Orvis is a mixture of water, sodium lauryl sulfate, was it a lauryl alcohol, and sodium sulfate, I think. The ingredients are listed on the Cameo webpage. And there's nothing wrong with it. As far as painting conservator goes, it just foams like crazy. So as you clear, it just turns into foam. The foam redeposits. So you just clear and clear and clear to get it off.
And if you're hosing off an outdoor sculpture of a horse or hosing off a horse, you can clear that foam away really easily. It's just that you can't, as you try to clear it on a painting, you agitate it more and more and make it foam more and more.
We also use Orvis and mineral spirits too, so that it cuts down the foamy.
Right, yeah, so you're kind of using some of the surfactants power with the mineral oil. And actually, if you mix two surfactants, you can lower the HLB to get a mean HLB, which is what you've just done by adding a little bit of mineral spirit, or you can even do like mineral oil, which is actually something that works.
Ooh.
Something like Dust Off. Dust Off is a cleaning product that works well, and it's basically just mineral oil, and it removes greasy, sooty material. One thing with Orvis that you have to watch out for, and this is why I think Orvis has a bad reputation, is that going above the 10 times critical micelle concentration is where you start to get problems with residues that are essentially permanent. When you go above the 10 times CMC, you start to form what are called rod micelles, which are very different structures from regular spherical micelles. And so those can form residues inside bronzes, particularly. I've seen this a lot, that will come back over and over and over, no matter how much you clean them. You pretty much have to scrub them away physically to get those residues out. So when you're out cleaning a big sculpture, even though you're doing a lot of work, you have to carefully measure out how much Orvis you're using, so you're not using too much in your solution.
The other thing, since it's an anionic surfactant, it can form soaps with calcium and magnesium. So if you're using hard water, if you're washing off your soapy sculpture with tap water, there is a good chance you'll be forming calcium salts, basically a bathtub ring. And whether it sticks on the surface or not is another issue, but a bathtub ring is a bathtub ring, and those calcium salts, until you bring the chelator onto them. And actually, citrate's not a good chelator for calcium salts because calcium citrate's not particularly water soluble. So for calcium materials, it's better to use EDTA or DTPA. But it's definitely, that's something to remember when working with Orvis. The other thing to mention is you can make, rather than Orvis, you can get sodium lauryl sulfate and use that as a starting material. So you don't have the sodium sulfate and the lauryl alcohol in there as well. The one thing, really odd thing about pure sodium lauryl sulfate powder is, I don't know what it's called when it makes you sneeze, but if you open a bottle of it, everybody in the room starts sneezing until you mix it in water. So.
Chris, can I ask you a question about held soap? I think you told me that it contains deoxycholic acid or a deoxycholate, and why held soap is not recommended?
I don't know what held soap is, so it may
It's
have
an
been.
oxgal. Apparently, it's an oxgal soap, and it does an amazing job at. I'm just wondering why we shouldn't really look into it. I've used it on, I guess, after 4 days of testing various materials on cleaning a Thomas Wilmer Doing mural at the Brooklyn Museum maybe 20 years ago. I used the oxgal soap that I brought back from Germany, and after 4 days of testing various materials, it's the only thing that took the dirt right off immediately.
I'd be really curious as to what it is.
Yeah, I think
probably have
maybe
some-
one should look into it, because it was a lifesaver in taking smoke, dirt from the Thomas Wilmer Doing mural where nothing else worked. It's just worth looking into, I think.
How do you spell it? H-E-L-D?
HELD. It's an oxgal soap, and apparently the manufacturer has changed the name. It's an oxgal soap, and I worked recently with it, and apparently I have a bar of it that's over 35 years old, and I'm still using it. And it was pretty amazing taking the soot off where absolutely nothing else worked.
Well, before we move on to the next question, one of the last things that you can look into for general outdoor sculpture cleaning is a surfactant called DDAO. It's dimethyl dodecan 1-amine oxide, and that is a really nice biodegradable surfactant that's maintained at a neutral pH, and it works pretty nicely. It's very safe to use, so you can check that one out. So we had a couple other questions about replacements for Triton X100. So Surfonic JL80X, Helen asked that would be a decent replacement, but again, you're talking about replacing something that has a phenyl ring on it, something that's aromatic. And so we're transitioning to products that are safer to use for both us and the environment. But that said, Surfonic is a pretty good replacement.
So Luke, I really enjoyed your article in the recent WAC newsletter
Oh, thanks.
about the nanostructured fluids. And I just had a question for you about the MEK. You were using that to...
Next week, Mark, that's next week's topic.
Okay.
Yeah, if you can hold on to it for one more week, we're gonna...
That's fine. Yeah.
You'll learn more about nanostructure fluids than you ever wanted to.
Okay.
We're trying not to overwhelm people with too much content and too much chemistry in one night, and keep these to, and
So-
2 hours or so.
We'll be putting that paper up on the Modular Cleaning Program and Practice Facebook page. We just got it from Carolyn, so.
Mm-hmm. Okay.
There's been some talk about making a chart that, and I believe it's the chart, you're talking about a chart of surfactants. And I would suggest that before anybody make the chart, they check out the wiki that I posted the link to on the AIC wiki page, because I think that might be the chart that you're talking about.
Okay, and then Kristen asked about identifying rod micelles. You don't really need to identify it. When you get pretty far above 10 times CMC, that's the behavior of pretty much all surfactants that we would be using. So they form rods, and they become very difficult to deal with, and they don't really give any extra cleaning power. They also start to foam and sud and do all these other things that we generally want to avoid. Okay, so someone asked to repeat the name of a product. Is that the DDAO, the surfactant? It's N,N-dimethyldodecane 1-amine oxide. But DDAO is
That was on the exam tomorrow.
If anyone ever wants to know what the capital NN is in front of a name, it means that the methyl groups are attached directly to the nitrogen in the molecule. So that's the N on there. And then a lowercase n means normal. Are the rods stacked? Spheres are just rods. They're generally stacked. They look like columns, like straws, kind of like bundled together. We can get into that stuff more next time. We're going to talk about micelles, micelle shapes, what affects micelle shapes, and what micelle shapes are beneficial compared to others. And as a hint, MEK has a lot to do with that.
So stay tuned.
All right, if anybody has any last minute questions, you can throw them in the chat or unmute yourselves. All right, so we are going to wind down our session for this evening. So that's kind of like the basic introduction to surfactants. So next week, we're going to do part 2. So we're going to take the properties that we learned about today and learn how to design micellar solutions, so complex micellar solutions, microemulsions. We're going to learn about de-wetting and how to use micellar solutions to de-wet polymer films, which is how to remove a film without dissolving it. You can actually make it curl in on itself and float off of a surface. So we're going to really go deep into surfactant chemistry a week from today. So I hope we can see you all again then. And thank you everybody for coming. I hope you learned something.
Bye. Thank you.
Bye.
Thank you.